Welcome. Today we'll analyze a four-bar mechanism to determine the accelerations of its links and their angular accelerations. We're given the link length, an input angular velocity, and a fixed angle. Let's break down the problem step by step. Now, the four-bar mechanism with known links and an input angular velocity of 10 rads per second. Our goal is to find the linear and angular accelerations of links BC and CD. So first we'll need to perform velocity analysis before moving to accelerations. So the first thing we do is to draw the configuration diagram or space diagram to scale based on the given dimensions. And then we now calculate the velocity of B with respect to A, which is given as product of AB, the link, times the angular velocity of 10, and we get a value of 1.9 meters per second. Again, now using a suitable scale, we're going to draw the velocity diagram as I'm going to describe. So we pick the fixed points AD in one location as shown, and we are going to draw the velocity of B with respect to A looking for point B in the direction shown, and this direction is perpendicular to the link AB and the magnitude is 1.9 meters per second. And from the point B, we are going to draw vector BC, which is perpendicular to the link BC as shown. Finally, from the fixed point D, we are going to draw the vector DC, which is perpendicular to the link DC as shown. Now we can then get the values from the velocity diagram, and we can measure the velocity of C with respect to B. We get a value of 1.65 meters per second, and similarly the velocity of C relative to D, we get a value of 1.1 meters per second. We can now calculate the radial accelerations of the three velocities that we now have. So the radial acceleration of B with respect to A is given by VBA squared over AB and is equals to 19 meters per second squared. The radial acceleration of C with respect to B is given by VCB squared over BC, and it is equals to 9.72 meters per second squared. Finally, the radial acceleration of C with respect to D is equals to 4.32 meters per second. So again, using a suitable scale, we are then going to go ahead and sketch the acceleration diagram, which I'm going to explain. So we first of all, again from the fixed points, AD, we are going to draw the radial acceleration of B with respect to A as shown. And this vector is parallel to the link BA. It's parallel to the link BA. The direction is parallel to the link BA, and the magnitude is 19 meters per second squared. Then from that point B, we'll then now draw the vector BC prime to represent the radial acceleration of C with respect to B as shown. And the direction is parallel to the link BC, and the magnitude is 9.72 meters per second squared. From the point C prime, we're going to draw the tangential acceleration of C with respect to B, whose magnitude we do not know, but whose direction we know is perpendicular to the link BC. Again, I'll repeat that. From the point C prime, we're going to draw the tangential acceleration of C with respect to B, whose magnitude we do not know, but whose direction we know is perpendicular to the link BC as shown. Then from there, we go back to the fixed point, and now we are going to draw the radial acceleration of C with respect to D as shown, and the magnitude is 4.32 meters per second, and the direction is parallel to the link CD. From the point C prime prime, we're going to sketch the tangential acceleration of C with respect to D, whose magnitude we do not know, but whose direction we know is perpendicular to the link CD as shown. So where C prime prime meets C is a point C, and that therefore enables us to complete our acceleration diagram. So we can now then take the measurements that we require to solve the problem. So we measure the acceleration of C relative to B, and we get a value of 10.5 meters per second square. Also, the acceleration of C with respect to D, we measure it and we get 25.5 meters per second squared. We know now the tangential acceleration of C with respect to B is now 4.5 meters per second. We had the direction, but you did not have the magnitude. From there, we can now calculate the angular acceleration of B with respect to C, which is given by the tangential acceleration of B with respect to C over the link length BC. And we get a value of 16.07 radians per second squared. We also now have the value of the tangential acceleration of C with respect to D, and that gives us a value of 26 meters per second squared. And we can therefore get the angular acceleration of C with respect to D by dividing the tangential acceleration of C with respect to D with the link length CD, and we get a value of 92.857 radians per second squared.